Functions, Lesson 4, Inverse Functions. So you have come across the concept of inverse functions previously. They reverse the action of the original function. So let's choose some examples to have a look at. We'll start with f of x equals 2x plus 1. Now you may previously have learnt how to find inverse functions by drawing a forwards and then a reverse flowchart. So we start with x and it is multiplied by 2. We then add 1, which are the components of the original function. If I want to reverse this, I would subtract 1 and then divide by 2, which allows me to write down the inverse function, which is expressed as f minus 1 of x, as x take away 1 divided by 2. And that should make logical sense. If you multiply by 2 and add 1, to reverse that you subtract 1 and then divide by 2. Let's look at some other very simple examples. If f of x equals x squared, well, the inverse of squaring is, of course, square rooting. So you might write down f of x inverse, or f minus 1 of x, is the square root of x. Similarly, if your original function f of x equals sine x, then your inverse function could be expressed as sine minus 1 x. Some of you may have heard of a more formal definition of the inverse sine function, which is something called arc sine x, which you will learn about a little bit later on in more detail. So let's think about these functions in a little bit more detail. If I apply f of x to a value in the first example of 3, that means I multiply by 2 and add 1, which gives me an output of 7. If I then apply the inverse function to 7, well, 7 take away 1 is 6, divided by 2 gives me an answer of 3. So I get back to the beginning here, and it works very simply. So we'll always get back to our original input. Let's look at the second example. Now this one's a little bit more interesting because quite often when you're looking at the square root, unless you're very specific, we quite often define the positive and the negative root. So if I start with a value of 2 and apply the function f to it, I very simply get back to a value of 4. But if I then apply the inverse function, yes, I could get back to a value of 2, but I could also get back to a value of negative 2. So this raises the question, which value would the inverse function find? If I'm very specific and just define the positive root, then it would be 2. But if I say plus or minus root x, we create quite a problematic ambiguity here. What happens with f of x equals sine x, the third example? Let's imagine I start with an angle of 30 degrees. If I apply f to this, I reach a value of 0.5. But if I apply the inverse function sine minus 1 to 0.5, yes, I can get back to 30 degrees, but I can also hit 150 degrees, 330 degrees. So again, there's an issue here with ambiguity. Now, why does this happen? If we go back to the first example, f of x equals 2x plus 1. This is an example of a one-to-one function, which means for every input there is only exactly one output, and for each output there is only exactly one input. So there's no ambiguity here when we're defining the inverse function. whichever output we have chosen will always be mapped back to the original input. Now, examples 2 and 3 are slightly different. These are what we call many-to-one functions. So f of x equals x squared and f of x equals sine x are both examples of many-to-one functions. Which means that several inputs can map to the same output. So, for instance, 2 and negative 2 both map to an output of 4, for example 2. And in example 3, both 30 degrees and 150 degrees both map to an output of 0.5. So, defining an inverse function for a one-to-one function is easy. But defining an inverse function for a many-to-one function is something we have to think about a little bit more carefully. And so this takes us to the concept that an inverse function can only truly exist or be defined for a one-to-one function. So what do we do about functions such as y equals x squared and y equals sine x, which are clearly not one-to-one functions? They are, as we've said, many-to-one functions. And there is a way around this. We force these functions to behave like one-to-one functions by simply restricting their domains. So here we go. Here's a set of axes. Let's make sure they're fully labelled. And what I'm going to do is draw on the function f of x equals x squared in green. Here it is. And I'm going to identify this function so that it only exists for x greater than or equal to 0. So here we have what is called a restricted domain. Now look at the graph. Because we've only got a portion of the graph, it becomes very, very clear that it's now behaving like a one-to-one function. 2 will map, for instance, to 4, but there's no option for negative 2 because we haven't got anything on this portion of the x-axis. So by restricting the domain of f of x equals x squared, we turn it into a one-to-one function. We can now draw the inverse function, which I will do in red, which is f minus 1x, which is the square root of x. And officially, if there's no sign in front of the square root, so if it doesn't say specifically that it's a negative root, if there's no sign, this means, by convention, the positive root only. And that graph would look like this. So here's the inverse function, and here's the original function. And you will notice that they are mirror images of each other in the line y equals x, which is true of all functions and their inverses. Let's have a look at some examples. So we're going to do 3 different things with this function f of x equals 2x plus 5. The first thing that we're going to do is find its range for part A. Now, an easy way of doing that is to sketch this function. It's a straight line or a portion of a straight line. The domain is x is any real number, but x has to be greater than or equal to 2, which means if we input that into f of x, let's work out what f of 2 is. That's 2 times 2 plus 5, that's 9, which means the graph starts at the point 2, 9. So if we find this point, it's going to be approximately here. It's a filled-in circle, a closed circle, because we are including that point, and it's simply a straight line with a gradient of 2, So it would look perhaps something like this. So there's the graph y equals f of x. So the range of this function is y, or you could write f of x, is greater than or equal to 9. Now, the inverse function, we're going to draw this in green. F minus 1 of x. Now, if we're multiplying by 2 and adding 5, the inverse function is going to be very simply subtract 5 and divide by 2. You can sketch a flowchart forwards and backwards for this if you want to, but it is quite a simple example. So we are going to sketch the inverse function and find its domain and range as well. So let's have a think about what's happening here. If this represents f of x and this represents f minus 1 of x, let's think about the domain of f of x. So x is greater than or equal to 2. We'll start with integer values only. So 2, 3, 4, 5 onwards to infinity. We'll make it a little bit easier by just looking at integer values, although of course x could be any number from 2 upwards, integer or otherwise. So substituting these into f of x will create the range of f of x, which is of course going to be 9, 11, 13, 15, and so on. Now, f minus 1, the inverse function, is of course now acting on this as a starting point. So the inverse function acts on the range of the original function f of x, which means that the range, highlighted in green, of the original function f of x becomes the domain of the inverse function f minus 1 of x. So the inverse function has a domain which is x is any real number and x is greater than or equal to 9. Now, for the inverse function, if we sub in 9 into that inverse function, that's 9 take away 5 divided by 2, that gives us obviously a value of 2, which means the inverse function starts here at the point 9, 2. Now it's the graph of a half x minus 5 over 2, so a straight line with a gradient of a half, so it looks like that. So you can see hopefully that it's again a mirror image of the graph of y equals f of x in the line y equals x. So have a look at the two graphs sketched on the same set of axes. You may want to recreate them on your graphical calculator as well. So what's the range of the inverse function? Well, the range of the inverse function, if we look at its y-coordinates, is 2 or above. So its range is y is greater than or equal to 2. So let's think about that idea again. The original function f of x acts on a particular domain and results in creating a range. The inverse function acts on the range of the original function and takes us back to its domain. So the domain and the range swap over between the function and the inverse function. Let's look at another example. So we have f of x equals x squared plus 3. X is a real number and x is greater than or equal to 0. Note, this piece of information here restricts the domain of this quadratic function and turns it into a one-to-one function. So let's make a note of that. So that's a restricted domain which forces f of x to behave like a one-to-one function. Now, let's find the range of this function. If we're starting with x is equal to 0, so x has to be greater than or equal to 0, well, if we input that into the original function, so f of 0, that's 0 squared plus 3, which equals 3, which means the graph starts on a y value of 3, and that should make sense because it is a translation of the graph of y equals x squared by a vector 0, 3, so a movement 3 units upwards. So the original graph will look like this. So there's y equals f of x. Now its range is very clearly y is greater than or equal to 3. We can see that from here. Let's find the inverse function. Now it should make sense that if your original function is squaring and then adding 3, the inverse function has to involve the subtraction of 3 first of all, and then the square root. Again, if you want to draw a flowchart for this, we start off with x, it is squared, and we then add 3, so to reverse that for the inverse function, subtract 3, and then square root. And as you can see, we only start with positive x values, which are inputted into the original function, and so we will only end up with positive values when we take the square root for the inverse function. Now, let's sketch that inverse function. It's going to look like this, a mirror image in the line y equals x. And let's identify its range and domain. So let's think about the domain of the original function f of x. We apply this to values 0, 1, 2, 3. Again, I'm just writing in the integers here for simplicity. And this results in values of 3, 4, 7, 12, and so on. The inverse function then acts on these values and takes us back to the original domain. So I've shaded in yellow the domain of f of x and its range in green. But hopefully we can then see that the domain of the inverse function is this range of the original function, 3, 4, 7, 12. So our inverse function, we can write in its domain, x is a real number, but x must be greater than or equal to 3. And we can see that from the graph. We can fill in this value of 3 here. Now, the range of our inverse function, well, it's a set of values here, y greater than or equal to 0. And you can see that. Look at this inverse function. We're allowing any y value of 0 or above. Look at the y-coordinates, starting with the y-coordinate of 0 at this point here, and then all y-coordinates of above 0 there. So we can summarise this in general. If this is the domain of the function f of x will map that onto the range of f of x. The inverse function, f minus 1 of x, then takes us from its own domain, which is the same as the range of f of x, and then maps us to the range of f minus 1 of x, the inverse function, which is the same as the domain of f of x. So the domain of f of x is the range of f minus 1x, and the range of f of x is the domain of f minus 1x. And the other key point that we've highlighted is that the graphs of y equals f of x and f minus 1x are reflections of each other in the line y equals x. Let's have a look at how we can find the inverse function for a given function. We'll have a look at a few simple examples. Number 1, let f of x equal 2x minus 5 over 3. We're not going to worry about the domain and range just at the moment. So one way which you may have come across previously is the concept of writing out a forwards and then reverse flowchart. So x is multiplied by 2, we then subtract 5, and we then divide by 3. To reverse this, we then multiply by 3, add 5, and finally divide by 2 in this order. So our inverse function f minus 1x can be expressed as 3x plus 5 all divided by 2. Let's look at another simple example. This time we'll have g of x, which equals x squared minus 3. So we start with x, it's squared, we then subtract 3. To generate our inverse function, we reverse these steps, first adding 3 and then taking the square root. So g minus 1x is the square root of x add 3. The last example, h of x is equal to 10 divided by x. Now, this is an interesting one. The inverse function of this is also 10 divided by x, which means it's the same as the original function. So h of x equals h minus 1 of x. To see this, think about some numerical values. If you start off with the value of 2, and you input this into the function h, so 10 divided by 2, which gives you an outcome of 5, well, in order to return back to 2, you have to do 10 divided by 5. So that means h minus 1 of x is also 10 divided by x. And we have here a particular example of what we would call a self-inverse function, where the function and its inverse are the same function. Another example might be something like f of x equals 12 take away x. Have a think about this yourself and you will soon see the inverse to this is also 12 take away x. Now, this approach of drawing a forwards and then reverse flowchart to find the inverse function works quite well for the simple examples that we have seen so far. It does not work well for more complex examples, and in some cases it simply won't work at all. So we're going to have a look at a more systematic approach for finding an inverse function. Let's take an example to start with. We're going to look at f of x equals 3x minus 4 over 5. Now, this is actually such a simple example. We could really write down what f minus 1x is without too much thought. You can see that x is multiplied by 3, we then subtract 4, we then divide by 5. So to reverse those steps, we need to multiply x by 5, add 4, and then finally divide by 3. So we know that's the outcome that we are looking for. So let's look at this systematic series of steps that we can use. The first thing we're going to do is rewrite f of x as y for simplicity with the algebra that we will be using. So y equals 3x minus 4 over 5. We're then going to rewrite y as x and x as y, so essentially swapping these over. So we now have x equals 3y minus 4 over 5. So again, look at how x and y have swapped places. We're now going to change the subject of this formula so that y is the subject, i.e. so that the format of the formula is y equals. So we'll multiply it by 5 first of all. So we have 5x equals 3y minus 4. Add the 4. 5x plus 4 equals 3y. And then divide by 3. So 5x plus 4 over 3 equals y. And y is our inverse function. So f minus 1 of x is equal to 5x plus 4 over 3. And we can see that this final answer is the same as the answer we wrote down at the beginning. So let's run through those steps again very quickly. The first thing that we needed to do was to rewrite f of x as y, just for simplicity. We then swap over x and y, so y becomes x and x becomes y. We then rearrange the formula so that y becomes the subject. And finally, we rewrite y as f minus 1x because this is our inverse function. Let's look at a more complex example. F of x equals 2x minus 3 over 5 minus x. Now the first thing that you should notice is that x appears in this function twice, which means it would be impossible to draw a forwards flowchart and then even try and reverse this, because which x do you start with in the flowchart? So it's not feasible to use that very, very basic method for finding the inverse function in examples like this. We have to use the more systematic approach that we looked at just now. So let's start with the first step, which, if you recall, is to replace f of x with y. So we rewrite this as y equals 2x minus 3 over 5 minus x. Now we're going to swap every y for an x and every x for a y. So if we look carefully, we can see that y has become x on the left-hand side. On the right-hand side, x has become y. We're now going to change the subject so that it is y. So we want this to be rearranged to the format y equals. So we'll start by multiplying by 5 minus y. So we have x bracket 5 minus y equals 2y minus 3. Expand the bracket, 5x minus xy equals 2y minus 3. We are changing the subject to y, so we want to collect all the y terms on one side and anything that doesn't contain a y on the other side. So we have 5x plus 3 equals xy plus 2y, collecting the y terms on the right-hand side. We now have y appearing twice, which means we need to factorise on the right-hand side. So 5x plus 3 is equal to y bracket x plus 2. And then finally, the last step of this is to divide through by the x plus 2. So we have y equals 5x plus 3 over x plus 2. And lastly, for clarity, we will write out the inverse function f minus 1x as 5x add 3 over x add 2. So we are replacing y with f minus 1x. So that our notation is extremely clear. and here we have the inverse function. So let's review the 4 steps that we've worked through. Number 1, we rewrite f of x as y, which makes the algebra easier. You can see that rewrite here. Step 2, we interchange y and x. You can see this highlighted in red. Step 3, we change the subject to y, i.e. we rearrange so that we have the format y equals, and then our final step is to rewrite y as f minus 1x, and we can see that step over here. So you will have been wondering, why does this process work? And in particular, step 2, the interchange of x and y, why does that work? Well, let's think about a function here, y equals f of x, and let's think about the inverse function, which of course is a mirror image or a reflection of f of x in the line y equals x, which you can see in blue. If there is a point on the original function y equals f of x, which we'll call a, b, then the mirror image of this point, if we go across to the line y equals x and reflect down here, we'll have coordinates b, a. So if there is a point AB on the curve or the graph of f of x, then when you reflect in the line y equals x, you create the inverse function f minus 1x, and the coordinates swap over. So you can see the x coordinate here becomes the y coordinate, and the y coordinate here becomes the x coordinate. So x becomes y, y becomes x. And that's why step 2, we interchange x and y before we then work through the rearrangement. So we're going to finish off by having a look at how we can create some composite functions using the inverse function as well as an original function. And we will use the example that we saw earlier, f of x equals 2x minus 5 over 3, and we found its inverse function. So I'm going to start off by exploring the composite function f minus 1 f of x, which of course means that we're applying f first because it's closest to x, and then after that we're applying f minus 1. So let's work this through in stages. So this clearly means we're applying f minus 1 to f of x, which means we're applying f minus 1 to 2x minus 5 over 3. So what does the inverse function f minus 1 actually tell us to do in words? It tells us to multiply x by 3, then add 5, and then divide by 2. So multiply whatever your input is by 3, then add 5, then divide by 2. And of course, our input is this, not just x. So we have to replace x by this whole bracket 2x minus 5 over 3. So let's have a go at doing this. So this then becomes 3 lots of the input, so 3 lots of 2x minus 5 over 3. So we've done the multiplying by 3 part. We then need to add 5, and then we need to divide the whole thing by 2. Let's work that through and see what happens. So you can see clearly multiplying by 3 will cancel dividing by 3 here. So we have 2x minus 5 plus a 5 all over 2, which becomes 2x over 2, which becomes x. So we can see that f minus 1 f of x simply equals x. Think about why that makes perfect sense. Let's now have a look at these in the other order. So this time we'll look at f minus 1, x. Now this means that f minus 1 is being applied first and then f afterwards. So this is f of f minus 1 x, which is f of 3x plus 5 over 2. So let's look at the function f of x. What does it actually tell us to do? It tells us to multiply by 2, take away 5, and then divide by 3. So let's follow through all those steps. So multiplying this input 3x plus 5 over 2 by 2, first step done. We then subtract 5, second step done, and we then divide by 3, third step in place. I think we should have ticked these steps off earlier for the other example. Let's then work through the algebra. Similarly to last time, multiplying by 2 cancels out dividing by 2. So we're left with 3x plus 5, take away 5 all over 3, which simplifies to 3x over 3, which simplifies to x. So interestingly, we can see that f minus 1 of x also equals x. Now, there should be absolutely nothing surprising in either of these results. If you apply a function and then its inverse, you get back to the beginning. It doesn't matter whether you do the function and its inverse first of all, or the inverse and then the original function, because of course the inverse is the inverse of the original function, and the original function is the inverse of the inverse. So if you start with x and apply f to get to f of x, if you then apply f minus 1 x, you get back to x. Similarly, if we start with x and we apply f minus 1, we get to f minus 1x. If we then apply f of x, we get back to x. The function and the inverse are inverses of each other.